So guys, listen. Now our topic of discussion for today is going to be about bar magnet as an equivalent solenoid. So write it down. So we are going to say that bar magnet and a solenoid behave equivalent to each other. For that, so write down the heading. One minute. Okay. So bar magnet as an equivalent solenoid. So what we are going to do in this scenario is, if I'm going to take a solenoid, okay, so if I'm going to take a solenoid like this, then I will take the axis of the solenoid in this way, okay. Then the center of the solenoid, let us say it is somewhere over here, so that if I take the total length of the solenoid to be 2L, then this part is going to be L and this part is going to be L. Is that clear? Is it clear?
Yes, sir.
So now what we are supposed to prove is, we need to prove that a solenoid, which is actually a temporary magnet, behaves similar to a bar magnet, which is a permanent magnet. So how to prove it? Okay, but before that, you need to know certain facts with respect to a bar magnet. So make a note of it. So if I take a bar magnet, right, I have north pole here, south pole here. Then these poles have something called as magnetic pole strength. Okay, they have something called as a magnetic pole strength associated with them. So how do you define that magnetic pole strength as? Listen. So if I take the distance between the north pole and the south pole to be 2L, then the magnetic dipole moment of a magnet, the magnetic dipole moment capital M, is given as small m into 2L, where the small m is called as the pole strength and 2L is called as the magnetic length. 2L is called as the magnetic length. 1 minute. I hope you guys made a note of it, right? So I'm not sure why the paper is getting broken. how it is done. Are you able to understand what I'm trying to say?
Yes, sir.
So just give me a minute. Issues resolved. So this is what is called as pole strength. So how do you define pole strength as? M will be written as capital M divided by 12. So you can define it as the magnetic dipole moment per unit length. So if you define the magnetic dipole moment per unit length, you can call it as pole strength. So what is going to be the SI unit for it is ampere meter square per meter. This and this will get cancelled. You will get ampere meter. So ampere meter is going to be the SI unit of magnetic pole strength. Okay.
Yes, sir.
Right. Now, if you observe this expression m into 2l, this is something similar to P is equal to Q into 2A. Have you seen this? So where Q is called as a charge and 2A is called as the distance between the charges. And what do we call this as? This we call it as electric dipole moment. Right? Now, if I take an electric dipole and along the axis of the electric dipole, if I try to calculate the electric field, then the electric field along axial point is given as 2 into Kp divided by R cube or 2p divided by 4 pi epsilon naught R cube, which we'll call it as 1. In a similar way, if I replace an electric dipole with a magnetic dipole whose poles are N and S, and the magnetic pole strengths are M and M, then on the axis of this dipole, if I try to calculate the magnetic field on the axis of it, then what will happen is 2 will be the same 2. Instead of P, I'll have capital M, which is the magnetic dipole moment. Instead of 1 by 4 pi epsilon naught, I will have mu naught divided by 4 pi. So 2 into mu naught divided by 4 pi into capital M divided by R cube. So this is going to be the value of the magnetic field due to a small bar magnet on the axis of it. Is it clear?
Yes, sir.
So can you repeat this part?
Sorry?
So can you repeat this part?
Yes. See, 1 by 4 pi epsilon naught in electric field should be replaced with mu naught by 4 pi in magnetic field. Okay. So here if you observe, in this expression, for me to, so I'm finding the electric field due to a dipole along axial point. If I want to find the magnetic field due to a dipole on the axial point, then I need to replace these values. So 2 will be the same 2. Instead of 1 by 4 pi epsilon naught, I will write it as mu naught by 4 pi. Instead of electric dipole moment, I'll write the magnetic dipole moment. And instead of, and R cube is obviously the distance from the center to the point where you're trying to calculate the field. Okay. So I want you to remember this expression because this is the expression we are going to use to derive the magnetic field due to a solenoid on the axis of it. Okay. So listen to this carefully. Now, so coming back to this derivation, so what I will do is, I'm interested to calculate the magnetic field due to the solenoid at point P. So for that, from the center, I will consider a small current carrying loop like this, okay, which is at a distance x from the center and is of thickness dx. Okay, let's say the number of turns per unit length of the given solenoid is small n. So small n will be equal to capital N divided by 2n. Let me call this as equation number 1, which implies the number of turns in the small thickness dx is small n into dx or capital N divided by 2l into dx. Let me call this as equation number 2. Okay. Now, listen to this very carefully. Okay. So if I say this distance is r, the distance from the center of the solenoid to the point where you're trying to calculate the field, if I call that as r, then how much will this distance be? Okay, sorry. Then how much will this distance be? It will be r minus x, correct?
Yes, sir.
So from the end of the tip of the current carrying element to the point P, it is going to be r minus x. Then if I calculate the value of magnetic field due to the small strip, then what is it going to be? It will be mu naught I a square divided by 2 into a square plus x square the whole power 3 by 2. So you know this formula, right? Due to a circular current carrying loop, the magnetic field on the axis of it at a distance x is going to be equal to mu naught I a square divided by 2 into a square plus x square to the power of 3 by 2. Okay. So here, if you observe, if I take the radius of the solenoid to be a, okay, then I will have this value written as mu naught into, in the place of I will write it as small n into dx into I into a square divided by 2 into a square is the radius square plus the distance from the current carrying conductor to the point V, which is r minus x the whole square. Okay, now you can remove this expression. Okay, so this is a very, very, very important expression. If this is not clear, you cannot proceed. Okay, so this is the value of small dB. Here you have to note the point that r is very much greater than a and r is very much greater than x, which implies r minus a is approximated to r and r minus x also can be approximated to r itself. So when that is a scenario, here I can approximate it to r. Similarly, so dB I can write it as mu naught into n into I into dx into a square divided by 2 into a square plus r square the whole power 3 by 2. But remember, R is very much greater than A also. So R square plus A square can also be approximated to R square itself. So it will become mu naught Ni A square into dx divided by 2 into A square to the power of 3 by 2. So how much is going to be the answer? Mu naught Ni A square divided by 2A cube into dx. Sorry. This is R square. This would be R cube. And this will be the value of dB. Okay. Now, if I want B, I will integrate on both sides with respect to x. So when integrated, B will be equal to integral of mu naught Ni A square divided by 2R cube into dx. If you see where x is varying from, then x is varying from minus L to plus L. Then x is a value varying from minus L to plus L. So if I take those limits minus L to plus L, then I'll get the value of B as mu naught Ni A square divided by 2R cube into integral of dx from minus L to L, which is equal to mu naught Ni A square divided by 2R cube into 2L. Okay. Is there any doubt in this?
No.
Okay. So when I say B is equal to this value, then small n into 2L will be equal to the number of turns. Okay, I can write it as mu naught into capital N into I into A square divided by 2R cube. So multiply and divide it with 2 pi. So when you do that, I can write it as 2 mu naught into capital N into I into pi A square divided by 2 pi into 2 pi 2R cube will be equal to 4 pi R cube. Okay. Now, if you observe this part of the expression, then B will be equal to 2 times mu naught into Ni into pi a square is area. So can I write that as the dipole moment itself? So 2 times mu naught m divided by 4 pi r cube is going to be the value of magnetic field due to the solenoid on the axis of it. And if you observe, this value is exactly the same as the axial value due to a bar magnet. Okay. So this is the value of magnetic field due to a bar magnet on the axis of it. Okay. And this is the reason why we can say solenoid is equivalent to a bar magnet. So I hope everybody is copying it.
Yes, sir.
Right? Just give me a minute. Yes. So with this, we are done with the first part of the chapter. Now we'll learn about the magnetic properties of materials. Okay. So before we learn about the magnetic properties of materials, just yeah. So there are certain terms which we are going to see. Okay. So as I told you, this chapter is divided into three parts. The first part is about bar magnet. The second part is about Earth's magnetism. And the third part is the magnetic properties of a material. Okay. So here the magnetic properties of a material means if I give you a material, then how will you magnetize that material is what the question is. Okay. So for which there are certain terms that you need to understand first. First is you have something called as magnetizing field. Suppose I have a material, okay. So last class I would have told you one point. If there is a material, a magnetic material, when you rub it against a magnet, when this is rubbed against a magnet, then what will happen is the magnetic material will start acquiring some magnetism, right? So who will acquire? The magnetic material will start acquiring some magnetism, right? And that value of, right, and the material that is observed is called as magnetized material. Okay. So to magnetize this material, what do we need? We need a field which can create magnetism in other materials. And that is what is called as magnetizing field. That is, when you take a magnetic material and if you take that magnetic material and place it in a magnetic field, then what happens is there is some magnetism induced in that material. Okay, so there is some magnetism induced in the material. So the magnetic field that induces magnetism is called as magnetizing field. So if you take an example, right, you have a solenoid, for example. So inside that solenoid, let's say you're placing a soft iron rod. Then what will happen as soon as you pass current through the solenoid, there is a magnetic field produced inside the solenoid whose value is mu naught into small n into I. This mu naught into small n into I will have the tendency to create magnetism on this so-called soft iron. Okay, then this mu naught into n into I is what is called as magnetizing field in this scenario. Is that clear, guys?
Yes.
Okay. Second point is we'll be learning about magnetic induction. So what is magnetic induction? Now, once the magnetizing field creates a magnetic field inside the soft iron, then we can say magnetic field is induced, right? So magnetic induction basically means the total value of magnetizing, the total value of magnetic field that is there due to the magnetizing surface as well as the induced surface. Okay, for that let's try to read a story. So as shown in figure, suppose a toroidal solenoid is wound around ring of magnetic material. So magnetic material here means do not confuse with magnetic that the material already has magnetism. No, the material is such a way that it can exhibit magnetism. Okay, is wound around a ring of magnetic material. Then under the influence of the magnetizing field B naught, the magnetic moments of the atomic current loops of the magnetic material tend to align themselves with or against the magnetizing field. Means what can happen is, suppose this is an iron rod, okay? This is an iron rod. I place it in the presence of external magnetic field. So let's say there is a magnetic field existing in this direction. And when you place this material in the presence of the external magnetic field, then small dipoles present in this will start aligning themselves either in the direction of external magnetic field or in the direction opposite to the external magnetic field. Okay, either of them will definitely happen. So it will get either aligned along the direction of magnetic field or in the direction opposite to the magnetic field. When this kind of a scenario occurs, then it gives rise to a net current on the surface of the material. So the material which is getting magnetized will have some current present on top of it. And that current is called as magnetization current, which is represented by the symbol IN. Okay. And this current, which is getting induced on the surface of the material, will induce a magnetism within this material itself. Okay, which is given by the symbol Bm. So here, if you observe, we are talking about two fields. One is called as B naught, and the second is called as Bm. Ba naught is the magnetizing field, and Bm is the induced magnetic field. Okay, if you observe the value of Bm, then Bm will be equal to the same mu naught times n into I into m. Okay, it is mu naught times small n into Im. Okay, this is what is the value of the induced magnetic field. Then what is magnetic induction? Then magnetic induction is given as the sum of the sum of the magnetizing field plus the sum of the magnetic field induced. So B naught is the one which is creating the magnetism. Bm is the created magnetic field. The sum of these two in vectors is what is called as magnetic induction. Okay. So if you're done with this, So, if you observe the SI unit of magnetic induction, the SI unit of magnetic induction is either Tesla, or you can call it as Weber per meter square, which is also equivalent to Newton per meter per ampere, or Joule per ampere per meter square. Okay. The next value is, we need to calculate the magnetizing field intensity. Means we have a magnetizing field which is given as mu naught into N into I. Right? So we have a magnetizing field due to a solenoid which is written as mu naught into N into I. If mu naught is called as the permeability of free space, then the small n into I is what is called as magnetizing field intensity, which is given by the symbol capital H. So the ability of magnetizing field to magnetize a material medium. Okay, the ability of magnetizing field to magnetize a material medium is decided by the strength based on which the material can magnetize another, which is called as magnetizing field intensity, or simply magnetic intensity. Okay, then how do you define it as? It is defined as the number of ampere turns flowing around the unit length of the solenoid required to produce a given magnetizing field. So the number of ampere turns it is the number of ampere turns per unit length. Okay, capital N by L is what is written as small n. So small n into I is what is called as magnetizing field intensity or magnetic intensity, and it is represented by the symbol B naught. It is given by the formula B naught divided by mu naught. And what is going to be the SI unit of magnetizing field intensity? The SI unit is going to be ampere per meter. Okay. The next one is called as intensity of magnetization. Do not get confused with magnetic intensity and intensity of magnetization. So magnetic intensity is the intensity of the input value. Intensity of magnetization is the intensity of the output value, how much a material has got magnetized. So when you take a magnetic material and when you place it in magnetizing field, it gets magnetized, no doubt in that. But when I say it is getting magnetized, there is a dipole moment created inside that magnetic substance. So if you are able to calculate the net magnetic moment developed per unit volume of the material. So if I take a material which is getting magnetized, okay, in that material, if I calculate the net dipole moment per unit volume, so the net dipole moment per unit volume, if I'm able to calculate, then this physical quantity is called as the intensity of magnetization, or in simple terms, you just call it as magnetization. That's it. Okay. So are you guys following it?
Yes, sir. Yes, sir.
Okay. Now listen to this carefully. You know what is magnetization current? Magnetization current, or the surface magnetization current, is the current that is flowing on the surface of the magnetic material. If you say IM is the surface magnetization current, 1 minute, charge is over, 1 minute. Now listen. If IM is called as the surface magnetization current setup in a solenoid of cross-sectional area A and having n turns per unit length, okay, then the magnetic moment developed per unit length. So what is the formula for magnetic moment? So magnetic moment developed per unit length of the solenoid is given as capital N into IM into A divided by L. So what is capital N divided by L? It is small n. So small n into Im into A will be the amount of magnetic dipole moment developed per unit length of the solenoid. Then what will be the magnetic dipole moment per unit volume that will get created? So n into Im into A divided by what is going to be the volume of that material? That's what we need to find out. So volume of the material will be A into 2L, because when you consider a bar magnet, right? How do you take the length of the bar magnet 2L and the area of cross section is taken to be A? So this and this will get cancelled. Then small n into Im has a particular value. So we know this value, right? The induced magnetic field is mu naught into small n into Im. So small n into Im, how can you write it as? So small n into Im, you can write it as mu naught into capital M. So what we are trying to say is this value is there. No, the second equation we saw Bm is equal to mu naught into small n into Im. That can also be written as Bm is equal to mu naught into the intensity of magnetization. Okay. Now, when you write the magnetic induction, right, then you will get the net value of magnetic field produced is B naught plus Bm, and B naught is written as mu naught H and Bm is written as mu naught into capital M. So this can be written as mu naught into capital H plus capital M. Okay, there is a very, very important expression, remember this, where capital H stands for magnetic field intensity and M stands for intensity of magnetization. Okay, the next is magnetic permeability. Now only we are seeing the definition of magnetic permeability in terms of all these values. So permeability means what? As the name suggests, it is the measure of the extent to which a material can be penetrated or permeated by a magnetic field. In the sense, the extent to which magnetism can be generated in that material is called as magnetic permeability. And magnetic permeability is represented as the ratio of magnetic induction to the magnetic field intensity. And the SI unit here is going to be Tesla divided by ampere per meter or Tesla meter per ampere. Okay.
Yes, sir.
So there are three more terms. Let's see them. So we saw what is magnetic permeability. Now we'll see what is relative permeability. Relative permeability is defined as the ratio of permeability of free substance, permeability of a material divided by permeability of free space. It is something similar to dielectric constant, epsilon by epsilon naught. In a similar way, Relative permeability is defined as magnetic permeability of a substance divided by the magnetic permeability of the space. Okay, it is a dimensionless quantity. Next, you have something called as magnetic susceptibility. In the sense, this is one of the important parameters that will tell you how fast or how slow a material can get magnetized. Okay, so magnetic susceptibility, if you see the name, it is mostly about the vulnerability of that material, the extent to which the material can get magnetized. Okay, it is the ability of a substance to take up magnetization when placed in magnetic field. Okay, it is defined as the ratio of intensity of magnetization M, that is the output divided by the input, and you represent it with the symbol chi. So it's called as chi M. It is defined as the ratio of intensity of magnetization to the magnetic field intensity. Okay, this is also a dimensionless quantity because M and H have both have the same unit. And the last term that we are going to see today is the relation between magnetic permeability and magnetic susceptibility. Right. So we know that the induced value of magnetic field is mu naught into H plus M. Right. So, but we can also write B is equal to mu into H. Take this and substitute it here. So mu H will be equal to mu naught into H plus capital M. So if I divide with mu naught on both the sides, okay, or I can take H outside, so then I'll have mu naught into H plus 1 plus M divided by H. H and H will get cancelled. So mu is equal to mu naught into 1 plus chi M. Okay. Now I can write mu as mu naught into mu r is equal to mu naught into 1 plus chi M. So mu naught will get cancelled. Mu r is equal to 1 plus chi M. This is also a very, very, very important expression. Okay. So these are all the terms that are related to the magnetic properties of a material. So once you understand this, okay, once you get clarity in this part, then I'll be able to teach you the next part of the chapter, that is the different kinds of magnetic materials or magnetic substances. One is paramagnetic, diamagnetic, or ferromagnetic. Okay. And the last part of the chapter that is left out is Earth's magnetism. If possible, I'll try to complete it by tomorrow itself, or else we'll take one more class to do that. Is that clear? So I hope
Yes.
everybody has taken notes properly.
Yes, sir.
Okay. So that's it from my side for today. I'll see you all in the next class.
Yes. Thank you, sir.
Yeah.
Bye, sir.
Bye.
Thank you, sir. Bye, sir.